Good evening, everybody. Welcome to week 9, I believe it is. Oh my goodness, week 9. For this week, we will be leaving formal regression, but not exactly as you'll see it as we get through this week. Now we start in what is like the second half of the course with quote unquote ANOVA topics. So things will shift a little bit, but a lot of the ideas from regression and basically what we're doing will be the same thing. We're going to be talking about things a little bit differently, using different words, but still basically trying to answer the same kinds of questions and thinking in the same way. So there'll just be a few new big ideas to learn, and hopefully it won't be too big of a deal as we get there. Well, for this week, I put a lot of effort into making 2 different guides and having a very nice step-by-step, high level of description and annotation in the help and tips file. And reading through all of it, I thought, given all of that, I probably don't need to waste your time talking a lot and just sort of reading things. Hopefully everything here is pretty step-by-step, blow-by-blow. If you just put in the patient time to read through it, process it, that should be good, and I think that'll be efficient. You can process it at your pace instead of my trying to go explain every little thing that's through here. And yeah, so I put a lot of time into this, and hopefully that will be very useful for you. And of course, I'm happy to take questions at any point about anything. But what I at least want to do is provide an overview of what these topics are and what this week's stuff is about and what the R script is about. So in general, what we are doing now and what we will do this week is starting with something called one-way ANOVA. And again, I go through all the little details of where it sort of comes from, why we call it that. So let me boil the main ideas down. What we're doing with ANOVA, we are still answering the same kinds of questions. We're still asking whether or not a particular explanatory variable explains a response variable. That's still the main idea. What ANOVA is in practice is asking specifically whether or not there are group differences along some response variable. That's really all it is. We ask for some categorical variable, some grouping variable. Are there average differences in whatever it is we're measuring? So for the example that I use, it's a made-up example, and I fabricated data. For the example I used in my guide, I just made up a situation and said our response variable is heart rate. And we want to ask, does the average heart rate vary significantly depending on what kind of study group we put you in? So this could be thought of like some kind of a health study where there are 3 study groups of, say, walking, sitting, and running. And I just made these up, and they're explained here. And we can ask, well, for individuals in the sitting group versus individuals in the walking group versus individuals in the running group, for whatever study context this is, do they have different heart rates on average? Are there significant differences in their average heart rate? Really what this is a regression with a categorical variable, which we just did in week 8. Or similar to regression with an indicator variable, except that only had 2 groups. The difference between regression and what we're doing now with ANOVA is that we are not necessarily trying to just load up a bunch of explanatory variables to explain something. Instead, we want to see for a very specific particular factor, a specific type of categorical variable, whether or not there are group mean differences. And you can think of it in terms of there are big questions asked about race, ethnicity, and certain health outcomes, or certain achievement outcomes, education level and certain outcomes, various gender studies and certain outcomes. When we start to think of just one or two categorical variables and whether or not there are group differences along some kind of response variable measure, that's thought of as quote-unquote ANOVA techniques. But really, it's just doing regression. It's just thought of in this different way. And in short, to just sort of give you the punchline, the reason that these two terms exist is because different fields think about statistics in slightly different ways. And so they have different terms for things. But really, regression is ANOVA. They're the same coin. We're just looking at two different sides of the same coin. As an overview of some of the key differences, though, when we write a regression equation, we know that we have some response variable, and we have our independent variable, our explanatory variable, and we have some coefficients. And we've spent a lot of time talking about what those mean. The ANOVA way to write a theoretical model is like this. Y still stands for the response variable. This Greek E still stands for random error. The difference is in how we think about what is going on in the middle of the model. What the ANOVA model shows us is it starts at what is called the grand mean. The grand mean is the average value of the response variable across every single subject in the study. It is the average response value, the average Y, for every individual in the study. That's why we call it the grand mean. The second part of the model is called the group effect. What this is, this group effect takes on a different value depending on which group we're talking about. This group effect says, starting at the grand mean, I either go up or I go down by some amount to get to the value of the response variable for that particular group. What that means, say for the example of our study here, our heart rate and study group study, is that I have three groups: sitting, walking, running. Therefore, I have three different group effects. What this means is that when I want to think about my ANOVA model for this situation, all I have to do is say, well, my response variable is heart rate. I know that I can find the average heart rate for every single person in my group. And then I want to estimate how far above or how far below my grand mean I need to go to get to the average heart rate value for a particular study group, for sitting, for running, for walking. So that's how the ANOVA model is set up. And I encourage you, again, I'm not going to go blow by blow here. I encourage you to just read through and see how each of these examples works for this situation. I just want to give you the high level overview of these things. What this means is we have different hypotheses as well. If you remember from regression, our hypotheses on our individual were on our individual coefficients. Beta 1 is equal to 0. Beta 2 is equal to 0. Beta 3 is equal to 0. Well, when we do a one-way ANOVA, and one way just refers to the fact that we're doing one factor at a time, we're just looking at one explanatory categorical variable. Our null hypothesis for a model is simply that every single group effect is 0. In other words, there are no differences between groups. There's no group effect. Every group just takes on the same value, the grand mean. So that's our null hypothesis, is that there are no group effects, that they're all equal to 0. The alternative hypothesis is that, well, there is at least one group effect. There is at least one group that's different from 0. And we'll hop over to the R script in a second to just look at a quick example of that. And I run through in detail, big detail, an example here. When we run an ANOVA, I encourage you to look at page 233 in the book to see how the results are organized. Those results are how the output looks in R. So we'll see that in a second. But the general table is there on page 233 in your book. And that's how we organize the results of our ANOVA. And all the nitty-gritty detail of each element is there. The key point with how we think about ANOVA is that our null hypothesis just says whether or not there are significant group differences. It doesn't actually say which groups are significantly different from each other. When we run a basic ANOVA, as you'll see, we know whether or not there are significant differences between groups in general, but we don't know without putting in more work which groups are actually statistically significantly different from one another. So without doing any more work, in summary, we have a different model for ANOVA. We care about group comparisons. We're testing whether or not the groups within our categorical variable have some sort of effect that are different from 0. And if we do find a significant result, we know that our categorical variable is statistically significant. But we don't know exactly, from a quick analysis, we don't know exactly which groups are significantly different from one another. Well, before we do anything else, we can check assumptions, just like we did in regression, because we're asking the same sorts of questions. We're addressing the same kind of research. We have to have our model and our data meet certain assumptions. Because we're not doing linear regression per se, because we're not trying to fit things on a scatter plot, because we're just looking at group mean differences, we don't need to worry about linearity or linear fit anymore. So that assumption does not apply in ANOVA. Instead, we look at independence the exact same way like we did before. We look at normality of the residuals and the errors just like we did before. And we check constant error variance. But now we have something nice with constant error variance. Instead of looking at a scatter plot of residuals, which you can do, we can actually check the variance or the standard errors of our study groups. That's what we care about. We want there to be constant variance between study groups. And we do that by taking the ratio of the largest group to the smallest group and comparing it to 2.